charges and magnetism? Yes, we know that due to current, magnetic field produces. Yes, we have obtained equation for magnetic field due to a long wire, a long straight wire, inside, outside and on surface. Now next important topic is in this chapter, and for yes, next chapter, that is magnetism, is the solenoid. Now what is solenoid? Okay, why solenoid is used? Okay, that we will see in this lecture. Okay, yes, there are two types of solenoid: long solenoid and solenoid having finite length. In this chapter, in your NCERT textbook, you are given only long solenoid. It's theory, question based on it. Yes, for finite solenoid, what is equations, what is used, that I will explain. Okay, but right now, follow NCERT syllabus, that is long solenoid. What is long solenoid? Length is large compared to its radius. But what length, what radius? What is a solenoid? See, solenoid is a long wire that is in form of helix, like this. It is called solenoid. Clear about this? Yes, you know that spring. You know that spring. It is called solenoid. It is called solenoid. See, it consists of a long wire wound in the form of a helix where the neighboring turns are closely spaced. So each turn can be regarded as circular loop. So what is solenoid? It is definition of solenoid. Again, it consists of a long wire wound in the form of a helix where the neighboring turns are closely spaced. So each turn can be regarded as circular loop as shown in figure. Clear about this? Okay. Now, each and every turn is regarded as a circular ring. We know that when current is flowing from circular ring, when current is, see, if I connect this solenoid with a battery, if I connect this solenoid with a battery, see, current is flowing, see, current is flowing, current is flowing, current is flowing. Yes, that current is flowing. So yes, current is flowing from this turn. This turn behaves as circular ring, and we know that due to circular ring, magnetic field produces. Due to this ring also, magnetic field produces. Due to this ring also, magnetic field produces. So yes, from each and every circular loop, each and every turn, current is flowing. And see, current is flowing in the same direction. Yes or no? Yes, it is. So yes, due to this each and every term, magnetic field is produced. So we can say due to solenoid, magnetic field is produced. Okay, and how to find that magnetic field? See, the net magnetic field is the vector sum of the fields due to all turns. Okay, magnetic field due to this turn plus magnetic field due to this turn plus magnetic field due to this turn. So yes, solenoid is used to produce magnetic field. Okay, these turns are insulated from each other. Now, how magnetic field produces? What is direction of magnetic field? See, we will understand. If I have one ring, okay, remember, case of magnetic field due to a circular ring. Okay, current is flowing in this direction, I. It is its axis. We know that when current is flowing in this direction, on axis, magnetic field is in this direction. Yes or no? But see, there are some characteristics of magnetic field lines. Magnetic field lines, okay, they form closed loop. Yes, in our theory, we have discussed for magnetic field only for axis. But due to this circular coil, the circular coil behaves as a magnet. And yes, for bar magnet, you know what is magnetic field's direction. For bar magnet, if you remember that experiment, okay, we take white paper, take one bar magnet, okay, if you sprinkle iron particles, then they will arrange in a regular pattern. They will arrange in a regular pattern called magnetic field lines. So, this current carrying circular loop is identical to magnet, and for magnet, magnetic fields are like this. On axis, parallel to axis, okay, it is magnetic field, yes, but as I am moving like this, as I am moving like this above axis, it will be like this. These are magnetic field lines. These are magnetic field lines. These are magnetic field lines. Clear about this? These are magnetic field lines. And yes, they form close loop. They form close loop. They form close loop. Clear about this? Yes, they form close loop. So, it is magnetic field lines for one ring. It is magnetic field lines for one ring. If I am taking two rings, okay, near to each other. If I am taking two rings near to each other. If I am taking two rings near to each other, having same axis. Having same axis. Then see, magnetic field lines due to this. Magnetic field lines due to this. When they overlap, what happens? What happens? In this region, magnetic field lines will be like this. In this region, magnetic field will be like this. Okay. In this region, magnetic fields will be like this. Yes. For this, see, here it is. It is in this direction, this direction. For this, in this direction, in this direction. For this second loop, yes, it is in this direction, it is in this direction. Okay, for this second loop, it is in this direction, it is in this direction. Clear about this? Okay, yes, we have considered only two rings in which current is flowing in same direction. In which current is flowing in same direction. Clear about this? Clear about this? Okay, so yes, when you place two rings identical in shape and size, having same axis, then what happens? See, in this region, there are almost parallel lines. There are almost parallel lines. Yes or no? Means in this region, magnetic fields are parallel to each other. Remember, for electric field, when electric field lines are parallel, it is called uniform electric field. Here, in this region, magnetic fields are almost straight lines and parallel and equidistant. So yes, in this region we can say there is uniform magnetic field. Means inside solenoid there is uniform magnetic field. While outside what happens? See, it is one circular loop, one turn. It is another loop. At this point what happens? See, at this point what happens? Due to this loop, magnetic field is in this direction. Yes. Due to this loop, magnetic field is in opposite direction. Yes. Same loops, same current. So value of magnetic field is also same. Direction is opposite. So yes, in this region, magnetic field due to one loop is vanished by, is cancelled by its neighbor loop. By its neighbor loop. Clear about this? Okay, same thing happens here in this region. Okay, so if I place more and more rings like this, to see in this central region, in this interior region, there are electric field lines almost in same direction parallel. While in this region, magnetic field lines, they cancel out each other. Magnetic field lines, they cancel out each other. So what is conclusion? What is conclusion of this theory? If I have one solenoid like this, current is flowing in this direction. So yes, in each and every turn, current is flowing in this direction. Then magnetic field is only in this interior part. If it is axis of solenoid. See, these all arrows, they are in this direction. It means that magnetic field is parallel to axis. Parallel to axis. While outside solenoid, magnetic field is 0. Outside solenoid, magnetic field is 0. Clear about this? Clear about this? So yes, from these figures, now we can make some conclusions. See, it is clear from the circular loops that the field between two neighboring terms vanishes outside. Clear about this? What happens inside? But the field at the interior is uniform, strong, and along the axis of solenoid. Why strong? This pattern due to another loop, again this pattern, due to third loop, again this pattern. If you overlap side by side, you will find that this each and every magnetic field lines, they are in same direction. They are parallel. Yes or no? So yes, they add up. So it becomes uniform, strong, and along the axis of solenoid. See, this axis of solenoid. Clear about this? The field outside the solenoid approaches to 0. Exactly at this point is 0. Actually, for finite solenoid and for non-solenoid, there is some value of magnetic field outside. But in this chapter, in our syllabus, we will consider, we assume that the field outside is 0. The field inside everywhere is parallel to axis. So for solenoid, what is solenoid? A long wire that is found in the form of helix is called solenoid. It is used to produce magnetic field. Which type of magnetic field? Uniform magnetic field. Uniform magnetic field. For non-solenoid, inside the solenoid, magnetic field is uniform, parallel to axis. Clear. Outside solenoid, magnetic field is 0. Now, there is magnetic field inside solenoid. Then what is equation? How to find magnetic field inside this solenoid? So that is second question. Obtain equation of magnetic field inside very long solenoid. Obtain equation of magnetic field due to long solenoid. Yes, we know that. Due to solenoid, magnetic field inside is uniform, but outside it is 0. Okay, let it is one solenoid. It is one solenoid. Okay, current is flowing in this direction. For example, current is flowing in this direction. I. Current is flowing in this direction. Okay, you have to represent current only in one. Okay, so see. Current is flowing in this direction, so magnetic field is uniform inside and parallel to axis. While outside, magnetic field is 0. Outside, magnetic field is 0. Clear about this? Okay. Now I am taking cross section area of this solenoid. See, cross section of this solenoid. Cross section of this solenoid. Here it is. See, current is flowing like this. Means from this end, upper end, it is coming outside, and from this side it is going inside. Yes or no? So yes, here it is inside, outside, inside, outside, inside, outside, inside, outside. Here it is inside, outside, inside, outside, inside. Clear about this? Okay? Okay. Clear about this? And magnetic field, it is in this direction, parallel to axis. Magnetic field is parallel to axis. Magnetic field is parallel to axis in this direction. It is magnetic field. It is magnetic field. Now we want to find what is magnetic field inside. So for that, I am taking one ampere and rule. Okay, take one. Take a square loop, take a square loop of length L of length L. Okay, how? Like this. See, it is one square law. Like this. P, Q, R, S. Length is L. And then I am taking current element in this direction. Sorry, I am taking elements in this direction. Clear about this? Clear about this? Okay? So yes, it is one law. Square law as shown in figure. Now we will apply Ampere's circular law. Now apply Ampere's circular law. What is Ampere's circular law? Integration B dot dl is equal to mu 0 sigma I. Integration B dot dl is equal to mu 0 sigma I. Clear about this? Clear about this? Now how to find? See, first of all we will find integration B dot dl. Integration B dot dl is equal to, it is a loop. So for this loop you have to find what is integration B dot dl. Integration B dot dl over a closed loop means integration B dot dl from P to Q plus integration B dot dl from Q to R, P to Q, then Q to R plus integration B dot dl from R to S plus integration B dot dl from S to P. Clear about this? Okay. Now is equal to, see, here is from figure. B, magnetic field, is in this direction. This element is also in this direction. Yes or no? Means the direction is same. So for this PQ wire, for this PQ element, I can write this. It is integration B dl cos 0. Clear about this? Plus for this QR. See, magnetic field is in this direction, and this wire is in this direction. QR means they are perpendicular. So what is angle between them? It is integration B dl cos 90. Clear about this? Yes or no? Yes. Plus RS, it is easy. See, RS, it is outside. It is outside solenoid, and outside solenoid magnetic field is 0. Then yes, directly this term is 0. Clear about this? Plus here for this PS again, magnetic field is in this direction. This SP is in this direction. Yes or no? So it is again perpendicular. So it is integration B dl cos 90. Clear about this? Clear? So yes, I can write this as B. Inside solenoid at each and every point magnetic field is uniform. So I can take this B outside. Cos 0 it is 1, so it is only integration dl. Clear about this? Okay. Plus cos 90 0 plus 0, and here it is plus 0. Okay. Integration dl for PQ, what is length of this element PQ? It is L. Then I can write it is B. So what is answer of integration B dot dl? Its answer is, it is B. Now we will find mu 0 sigma I. Now we will find mu 0 sigma I. I will find sigma I. Sigma I means what? Sigma I means total current enclosed by Ampere loop. It is Ampere loop. See students, it is Ampere loop. Now see, in this region, there are numbers of turns. From 1 turn current flowing is I. From 2 turn current flowing is 2I. From 3 turn current flowing is 3I. Now do you know numbers of turns in length L? No. So for that we have to assume one quantity. Say let small n is numbers of turns per unit length. Numbers of turns per unit length. Understand? N is number of turns per unit length. So if length is unit, number of turns are n. Here what is length of this Ampere loop? See, it is n, the number of turns in this loop, in this ampere loop. Okay, for length L, number of turns are, for length L, numbers of turns are, so yes, numbers of turns are is equal to n. What is current flowing from 1 turn I, 2 turn 2I, 3 turn 3I. So what is current flowing from? NL turns. So total current flowing from enclosed by loop, ampere loop, sigma I is equal to, it is NLI. It is NLI. Now use Ampere's circuital law, that is integration B dot dl is equal to mu 0 sigma I. What is answer of integration B dot dl? It is BL is equal to, what is equation of sigma I? Yes, here it is NLI. It is N, yes, mu 0. Where is mu 0? Here it is NLI. L cut. So B is equal to mu 0 Ni. B is equal to mu 0 Ni. It is equation of magnetic field inside very long wire. Now see why mu 0? Because the region inside solenoid is air, so that's why it is used mu 0. If we replace medium region inside this solenoid, if we replace air with some another medium, then yes, you have to replace this mu 0 by mu. Mu 0 is permeability of free space. If you put any other medium, you have to replace that. Clear about this? So yes, mu 0, permeability of a free space, small n, remember small n, numbers of turns per unit length. See, if I have one solenoid, its length is L, total turns, total numbers of turns are n, then how to find small n? Small n means numbers of turns per unit length. Small n means numbers of turns, total numbers of turns per unit length. Clear about this? So B is equal to mu 0 Ni. Mu 0, permeability, small n, numbers of turns per unit length, Ni, that is current flowing from it. Clear about this? So yes, what is solenoid? Magnetic field due to solenoid, it is its equation. Clear about this? Yes, it is one important point. We will also see solenoid in next chapter, that is magnetism. Okay, watch regular videos, make notes, and if you have any doubt, any query, then contact me. Okay, and yes, subscribe our channel if you do not have, like, share and comment on videos of all teachers.